Hi, my name is Edward Ming.
And I'm Alec Northland, and today we'll be proving the equation angular acceleration equals torque net over moment of inertia.
So the equations we will be using today are torque net equals mgr, where we use mg to replace the force, and we will also be using moment of inertia equals the initial moment of inertia plus the mass times radius squared.
To find the angular acceleration, we'll take angular speed over change in time. So this is the system we'll be using to prove our equation. It is basically a PVC pipe on a rotating axle. Here we have a T-intersection with one pipe representing the radius and a weight hanging from it representing mass times gravity. We also have these two PVC pipes, which we will use to change moment of inertia by adding fishing weights at various locations.
So we will perform a quick demonstration of the system without having a modified moment of inertia. So we let the PVC pipes run, and we will calculate the angular acceleration, which allows us to measure the moment of inertia.
So here are the results from various trials averaged together. You can see that the time for a single revolution changes as it accelerates. So angular acceleration was found with change in angular speed over change in time. So our total time came to 12.125 seconds, and the final angular speed was found with 2 pi over the period length. And there at the bottom is the railroad track works. By the end, angular acceleration was 0.299 radians per second squared.
So we use the angular acceleration equation where angular acceleration equals the torque net over the moment of inertia, and we found the net torque by calculating the mass of the weight times the gravity times the radius of the PVC pipe. So we found it to be 0.167 Newton meters, and we used the moment of inertia equals the net torque over the angular acceleration previously found, and we calculated that to be 0.558 kilograms meters squared.
So this is our second demonstration. We have added two weights about 0.245 kilograms each at a radius of 0.25 meters from the center. This will modify our moment of inertia. We have also tripled the torque to give us an easier to read measurement.
These are the results of our experiment with two weights on the PVC pipes. We used the same angular acceleration equation as the previous one, and we calculated the angular acceleration to be 0.815 rads per second squared.
Okay, here's the calculated moment of inertia for our second test with the weights added. Calculated this with the moment of inertia from our first test times the mass of the weights times the radius squared from the axle in which they rotate upon. There are the calculations below. It works out to approximately 0.589 kilograms meters per second squared. We then set the first moment of inertia times angular acceleration equal to the second moment of inertia times angular acceleration over 3. This was to prove that our equation worked, and the second part is over 3 due to the fact that we tripled the torque in our second experiment. There are the calculations below. In the end, we got 1.67 Newton meters squared equals about 1.60 newtons times meters squared. We will talk about why they are different in the next slide.
So there may have been some flaws in our experiment. One, there could have been a lot of friction in the PVC pipe, like the metal rod, when it was rotating, and there may also have been errors in our timing due to a human error.
Another possibility is that the PVC pipe does not rotate at the center of the axle. This would mean that you are rotating its center of gravity up on a different point at which you are rotating it. That would mess up the results quite a bit.
So one real-life application that may have been related to this experiment is a baseball player with a bat So if the if the baseball bat has a lighter mass, it will have a greater acceleration and a smaller moment of inertia. You want to talk about the second?
Okay, another possibility is an airplane prop, which they want to accelerate it to a certain rotations per minute pretty quickly. They do this by moving the mass towards the center of rotation, which decreases the moment of inertia. In this project, we proved the equation angular acceleration equals torque net over moment of inertia. We did this by rotating a PVC pipe around an axle, using a weight as torque and moving weights along the axle to change moment of inertia.
Thank you for listening, and I hope you have a great day.